some Mongolian dessert.
Maybe, yeah.
What?
Maybe, yeah.
Did you try? That's the right color for you.
Probably 3D printed.
Ooh.
What?
Ooh.
Yeah, don't eat the desserts. Have this kind of colors.
Okay, welcome back, everybody. Looks like I found a new job as chairman. So it's a pleasure to introduce Rajesh Ganapathy with his talk, Are Dynamical Crossovers en route to Glass Purely Dynamic?
This is the first lecture that you know the title.
Exactly.
Yeah. All right.
Please, Rajesh.
Okay. Thank you, Luca, for the introduction. Okay, so this is my second UCGP, and I'm going to start with a little story that happened in the first one that Paddy put together. So we had a piece of work which was on de-vitrification. De-vitrification of colloidal glasses. It took us about 6 years to complete. We had this nice poster, and then I drag one of the theory giants to the poster, and he says, it's all very nice, tell me something I don't know, okay? So I hope that this is not going to be a repeat of that. I hope I really have something new to say. So I'm going to thank the organizers for this opportunity, Shrikant, Ranjini, Saint, and Rituparno. But I'm going to reserve my opinion about how much I like UCGP until tomorrow afternoon. All right. Okay. So the first thing is, this is not a problem that you give a PhD student. Okay. We have heard Jill talk, and this is not something you would want to go after. So what we had was a small sliver of an idea about trying to look at structure around particles that break out of cages, and that's the picture that I show you here. It's basically a density field, and you see this beautiful asymmetry that's coming about. And what it turned out was this had a highly non-trivial temperature dependence. And in hindsight, we ended up asking this question, and so I'm going to show you how we basically get this structure and what the T dependence of this structure was, right? Okay, so everything that can be said about this plot has already been said. And by the way, this is work done by Kamlesh, who's here in the audience. He's equally adept at doing simulations as well as experiments. He's co-guided by Walter, so this is work that's been going on for the last couple of years. Okay, so everything that can be said about this plot has been said. You can view it through different lenses, like Ludovic pointed out. The one that's been keeping us going is to look for experimental ways or methods that allow us to look at order in these systems, or uncover means to probe order in these systems. What's fascinating is that this is not just relevant to the glass problem. So if you do find these methods, it's got a broader reach, okay? And that's what's been fascinating. So this is a plot in which I'm plotting for you the alpha relaxation time versus the inverse temperature. And the way you would pick this out is you would do, for instance, you would do something like an intermediate scattering function or a density-density correlator. And the first dynamic crossover that you encounter is basically you start cooling the liquid and you start developing the shoulder in your intermediate scattering function at some temperature, all right? And that temperature we identify with the onset temperature. And that's typically, so that's now well agreed upon that it's associated with cage escape, or with the onset of cage formation and cage escape, all right? So as you cool the liquid further, what happens is in this window after T onset, as you continue to cool further, you start seeing dynamically heterogeneous, dynamical heterogeneities. So these are beautiful real space experiments that captured these heterogeneities more than a quarter of a century ago. So you can associate a length scale with these dynamical heterogeneities, and it grows. And around TC, what happens is that, so these were experiments that we did a couple of years ago, is around TC, inspired by theory and numerical work by Kobe and Ludovic and others. And what we found is that around TC, these dynamical heterogeneities, oh, by the way, this was a two-dimensional experiment, so we're just tracking particles in 2 dimensions. And what we found is that if you look at the shapes of these clusters that form these heterogeneities, they go through this sort of a string to compact transition, all right? And that's something that happens at TC. And this is more recent work, but even 25 years ago, people had already started from a geometrical interpretation of the P of the landscape. There was already evidence that something non-trivial happens at TC. And one could basically, take the derivative of this plot. You could start seeing that there is a crossover in the way the energies evolve with temperature. It's associated with the mode coupling. You could associate it with the diffusion to hopping sort of motion and stuff, okay? And both of these crossovers are generic to many, many glass formers. So it's worth understanding what's going on around here. But personally for me, the most definitive proof that this crossover exists came only 2 days ago in Jill's talk. And none of you had any questions about it. Okay, so I'm just going to take this as my starting point. I'm going to assume that the MCT crossover is set in stone, and we're going to go ask what happens around these crossovers.
About the fairness.
Right. And it says do not further discuss, so that's about the end of it. All right. Okay. So this is a clause that I always like to put in a talk. So that to the best of our knowledge, there has been no signature that you see changes in the structure. And by the way, the heterogeneities in these systems, the dynamical heterogeneities, show a lot of changes across these crossover temperatures. And even if you were to look at these heterogeneities, you do not see. All right? And this was some measurements that were, these were extensive measurements that were done in simulations, of course, by these people. And once again, you did not find changes in the heat capacity. Okay? So the way we're going to try and approach this problem is to rely on a recently developed approach. It was put forth by Zhang and Cobb about 5 years ago. And the idea is, so what I'm showing you here, so these are MD simulations of the standard Lennard-Jones mixture. So the pair correlation function is not showing any remarkable change as you cool from T to 0.4. But then what you do is to look at the structure in these systems. The clever approach that was put forth here is that you develop a local coordinate system. So in the local coordinate system, what you do is you take a central particle, put it at the origin, take a second particle, put it along the z-axis, and a third particle along the z-x plane. Okay? And all of these are big particles. Okay? So it's an 80-20 mixture. I'm doing it for all the A particles in the mixture. All right? And now what you do is you ask the probability of finding a fourth particle at a distance r theta phi. All right? So instead of doing the angle averaging, which is what the pair correlation does, this approach basically seeks out angular correlations. And what you have to do is you have to do it for every triplet in the system, and then you have to rotate the coordinate system, average it out, and then you get the structure. Okay? And when you do this, what you find is this sort of remarkable angular order that's there. So this is at t equal to 2, and you see that I am picking out angular correlations. This analysis is picking out angular correlations that extend well beyond what the pair correlation does. And for example, at t equal to 0.4, you see these correlations extend all the way up to 8 sigma. All right? And then what you can do is you can resolve these structures, and what they found is this is sort of an icosahedral dodecahedral structure. Please note that these are dual polyhedrons. So the what do you call the, yeah. So the pits of the first layer are going to be occupied by the next layer, which is going to be a dodecahedron. All right. So this very clear evidence that there is angular correlations extending all the way to the intermediate range. All right. And please note that the colors, one thing that I have to say here is that if you look at this patch, so what I've done is to project all of these particles onto the unit sphere, but when I'm seeing such a large patch at r equal to 8 sigma, what it means is it's not a single particle density field that I'm picking, it's a patch of particles that are actually having this sort of an order. All right? And once I have these density maps, what I can basically do is, this is a more beautiful rendering of it. So you're seeing the central particle go all the way out, and the colors are basically the icosahedral dodecahedral structure. And once I have this sort of density maps, what I can do is I can basically decompose them into spherical harmonics, find the dominant L values, all right? So I'm basically calculating the angular power spectrum, and I'm plotting for you the angular power as a function of R, and I'm showing it to you for all the L values that were calculated, all right? And what you find is based on what you visually observe in this analysis, as well as what you pick out from the signals, you basically see that it's consistent with this icosahedral dodecahedral order, all right? And this approach is order agnostic in its design, because you don't go impose any particular order. You look for all L values, and you find the ones that are pertinent to the structure that you're interested in, right? The question is, can this be done in experiments? So these were experiments that were done with granules. So what they did is, this is basically, you take granules in a container, you can do tomography of this container, you can get all the particle positions. This was done for different size ratios, so this is the distance, but this is done for different size ratios. You once again see this sort of angular order develop at large distances. We did colloid experiments. So this was athermal, so we went to colloids. So what I'm showing you here is the density at 3 different packing fractions. Once again, you see this sort of beautiful order, and the composition of the colloid mixture was identical to the Cobb-Anderson mixture. So it was an 80-20, roughly the same particle size ratio. And you once again see this sort of order emerge all the way to distances exceeding 5 sigma. And this is to basically address a question that Shrikant posed to me a while ago, which is, you can see this in all toy models of experiments. Can you really do this in real experiments? So what I'm going to fall back on is this basically a very nice technique that's still developing. So it's called atom electron tomography, in which you basically are able to resolve the positions of all atoms with a substantial contrast in their Z, in the atomic numbers. And if you can do that, you can basically reconstruct the diffraction pattern and get the positions of all the atoms. So this was done for a metallic glass in this particular paper, and these people were nice enough to put the coordinates out. So we basically analyzed them, and you once again see this beautiful order that's again developing here, except that we pull out medium range order extending up to distances exceeding 10 angstroms and so forth. So it's really extended, all right? So with granules, they don't move around much unless you excite them in some way. So these were just static packings. With metallic glass formers, I can reconstruct the positions of atoms, but I can't give you movies. The cool thing about colloids is I get to see movies of these. So what it means is that what we also did with the colloid experiments is to basically, from the trajectories of these particles, identify all the fast and slow particles. So what we do is we have this, so we find out the time at which it breaks out of a cage. So that's my non-Gaussian parameter. And at that particular time, T star, you identify the slow and fast particles. So we identify the top 10% slow and fast. And then what we're going to do is we're going to tag all particles in my fluid as basically fast and slow within the 10% cutoff. And please note that the mobility information is used only as a label on the particle. All right?
Is that how fast and slow is usually defined, 10%?
Yes. Yes. No, it's 10% is not a threshold that's universally. Yes. But you do look at, so there are ways in which what you can do is you also see hops coming out for the fast particles. You can define that as a threshold. It's not, but 10% is something that people routinely do, which is what we've done. Okay. So we're just going to use this information to tag the particles, and we're going to look at the structure around the slow and fast particles. All right. And so this is at 2 densities as a function of distance. This is the slow, this is the fast, and this is the difference, all right? The difference field is non-zero, which means the structure around the slow particles is more well-defined than the structure around the fast particles. It evolves with cooling, and it extends the intermediate range. So it's not just in the local neighborhood that differences are, it extends all the way to the intermediate range. And what one can ask is, one can decompose this density field again into the harmonics. So we look at 6 for the reasons I told you earlier, L equal to 6. And I'm plotting for you the angular power for both the slow and the fast particles. And what it shows is something which we didn't quite expect at that point, is that at very short distances, the angular power contained in the fast and slow is nearly identical. The difference is at intermediate distances, and then of course at very, very long distances, these differences vanish away, all right? So what we can do is, we can label all these peaks trivially, and we can find the ratios of these peaks, okay? And that's what I'm plotting for you, the intensity of these peaks. And what you see is that, of course, the difference is not 1 at even the smallest r, so there is some difference between the fast and slow, but the difference is maximal at intermediate distances, and it grows as you cool the system, all right? So as you go from 0.56 to 0.60, this extends to 4 sigma, right? And what we would like to do is basically use this toolkit, exploit this feature that we found, and ask if this approach is going to start telling us something about the structural change that we can see across. If at all it exists, can we pick it up, all right? So what we're going to do is simulations. So we're going to work with a modified BLJM mixture. Sarika already told you about why the modification is essential. So we equilibrate the sample for about 10 tau alpha. All of these are done in the NVT ensemble. And these are the tau alpha versus 1 over t for this particular sample. This is where I have doubts whether we can ever do this in colloid experiments. I don't think we'll have such a fine resolution of volume fractions to go probe this order. All right, I don't know yet. And for this particular sample, we know T onset. For this particular system, we know T onset and the critical temperature. And those are the 2 temperatures we want to watch out for as we move. All right. So we do it. So this is the modified potential. So one can ask, is the structure similar to the standard Kobe-Anderson? So we once again find this beautiful icosahedral dodecahedral order in this 4-point coordinate system approach. And what we do is we once again look at this dominant signal coming from L equal to 6. So what I'm showing you is the same for different system sizes at t equal to 2. What you see is that as you increase the system size, the resolution at far away distances gets better, as you would expect. But then what we're going to do is that we get a substantial dynamic range, which means that we're just going to stick to n equal to 32,400 particles, and then go ahead and see what happens. All right. And once again, for this particular system, what we will do is, I'm going to define a correlation length, which is from the decay of this S rho. That's called xi total. Because it's averaged over all particles in the system. Then I'm also going to basically look at the fast and slow, like we did in the colloid experiments. Okay, so the 10% fast are here. The 10% slow are here. The 10% fast are here. All right, and we're going to look at the structure around these particles as well. This is at t equal to 0.38, which is well below the mode coupling temperature. So this is the density map for the slow. This is the density map for the fast as a function of distance, and this is the difference field. The first thing that you see is that both the fast and the slow have the same symmetries. What is changing is the intensity of the signal, which is what you see here. And once again, we did this sort of analysis in which we were able to show that the difference is maximal not at nearby distances, but at intermediate distances. All right. So once we have this, it's all consistent with what we found in the colloid experiments. And now what I can do is, for the fast and slow particles alone, I can define my I can define S rho, and I can do this as a function of temperature. And what you always find is that the slow particles kind of ride above the fast ones, which is consistent with the better structure that I see. And now I can define 2 more static length scales. Static, I'm emphasizing that because I'm not using any time information apart from just tagging them. All right, we're going to call it structural length scales too. All right, so I have xi s, which is for the slow particles, and xi f for the fast particles, and I'm going to basically track the temperature dependence of all of these 3 length scales: xi total, xi s, and xi f. All right. And let's first look at the slow ones and compare it with what's happening with the fast ones. So this is my, so the squares are my, or all the particles in the system, and the 10% slow are right here. They're kind of riding up, as you would expect, on top of the xi total. But what's fascinating is that there seems to be a sort of a step increase here, and I can zoom in on that step. All right, it's right here. All right, and what I can do is, it happens close to TC. What I can also do is, I can now try and do a more simple analysis, which is just to look at the pair correlation function for the fast and slow, and try to get a similar length scale from the decay of the pair correlation function, and I see nothing. Okay, so this is seen for the same temperature window, the zoomed in plot here, and within the noise, so it's on the same system. All right, same number of particles going into the averaging and all of that. I don't see anything in the pair correlation function, except I see a small step in xi s that happens close to TC. All right. So what one can do is to basically fit this to a step function. All right, and
What do you have much more noise on the pair correlation than on
so this is.
This is very much resolved, right?
This is very much so. The noise.
So we have to trust the.
Oh, these are from 4 independent runs, jackknife errors. Yeah, so the error bars are what they are, right?
Rajesh, why are you calling that as a step? Because then you can find steps in many other data.
Why am I calling that particular step? Okay. So I'm going to come to that. I'll show you the data. Let's go to the next slide. After I finish this one, maybe it'll be a little more convincing. All right, so what we can do is the following. We can try and fit a step function to this on a linear increasing baseline. And what you find is that the signal to noise ratio that this 4-point analysis gives you is about 10 times better, is about 9 times better, which means that if you assume it's purely coming from statistics, you need about 80 times larger data volumes to basically resolve this step, if it is purely statistics. All right? Okay, so yes. Now is your step. Yeah, Swarajit. That's your step.
No, the answer to Gilles' question I didn't quite understand, because it is surprising that that's something that you draw from the GFR, which is a much more easy quantity to calculate, seems to have large.
Yeah. So the way it works is the following, right? Okay. So when you consider this triplet, this 4-point correlations, what you do is you go to, so you have a central particle, you put a particle on top. That's by definition. Then you have to do it for all possible orientations, and that gives you the better averaging. So for every particle, I do 10C2 averages. Yeah. So and that already gives you a factor of 50, and what we're finding from the signal to noise is.
But I mean, that's not necessarily an independent sampling.
It's not. No. So the minute you. It's not an independent sampling, I agree with that. But then the minute you put a particle on top, the probability of finding it there is 1, and everything else you'll have to start asking. And when you go for a different configuration, so that changes, right? Yeah. All right. Okay, so Sarojit, so all I've done right now is to basically scale xi s by xi total. I don't see many steps, I see 1. Am I? Yeah? I'm sorry?
If you go back, I mean, it's 0.5. Yeah,
Yes.
It's even bigger, no? The step, no? It's not a step?
Okay, so that is not a window that we have looked at very deeply yet, but then we are not able to resolve it as well. But the ones that we're focusing on right now is basically what happens in this window here. Yeah. Kamlesh may have a better answer for this, but we can talk to him later. All right? So now all I do is now take the ratio of xi s by xi total. So in this window of interest that I have, and so that's basically taking out the baseline, and I see this increase. And what's interesting about this is that if you now just go to all the slow particles and cluster them and find the average cluster size, that peaks right near where the step is. All right? It peaks right where the temperature, at the temperature at which the step is. All right? And of course, after the step, you expect the rest of the system, as you cool it, to catch up and get better and better ordered. So the contrast between the slow and the fast is basically going to die down, which is why it's dropping back. All right. But the interesting observation is, besides the step, is the fact that if you now change the cutoff for your mobile particles, you go from 10 to 20%, what you see is the step shifts. Okay, you have to cool it further to see the step. And correspondingly, if you see where the cluster size of slow particles is maximal, it once again also shifts correspondingly. All right? And if you cool the system even further, it shifts even closer to TC. All right? So the takeaway from this is the location of the step coincides with where the cluster size is maximal, and the mobility cutoff shifts the step, and this is what we would like to understand. We have like a simple way of thinking about it. We don't know if it's fully accurate, but then the way to think about this, so let's look at the 10% cutoff. So what I'm showing you here is a cartoon rendering. So I'm looking at this particular point here. What we already know is that the length scale associated with all particles is already smaller than the one associated with 10%. So let us say that these are my clusters. They're kind of large, and we are at the verge of where the step is going to happen. And all that's going to happen is that when you cool the system further, these blobs, it's not the particles, they have an associated structure, which is the correlation length associated with them. These blobs are going to basically talk to each other, and that gives you this sort of a percolation sort of a thing that's happening. All right? And it's probably consistent with what's being said in these other studies as well, all right, by Epe. So now what happens is, now let's say that I change my cutoff and I go to the top 20%. Please note that this 20% basically includes all my 10% as well as the 10 to 20%. And these are the length scales associated with those. The 10 to 20, of course, is going to be smaller than 10, but larger than xi total. And those are what the blobs are. And so my average length scale is going to be a little smaller than what I would have gotten with just xi equal to 10%, with the 10% cutoff. What it essentially means is that I have to cool the system further so that these blobs can percolate. All right, and that tells you why the step is shifting. All right. Okay. Now the thing is, this is all for the slow particles. One can ask, what are the fast particles doing? And please note that the fast particles are the one that basically had this morphology change as you cool the system. All right. So if at all you see something, one would have thought that this is going to be more pronounced for the fast particles. And what you see for the fast particles is basically nothing. Right across T naught or right across Tc, you do not see any change in the way the slow particles showed it. All right. And we can change the cutoff, and it doesn't matter. All right. So to understand why this might be happening, let's go back to how we define the local coordinate system. All right. So what I've done is that I've gone to a single particle. So this is one single particle that I'm interested in, which is the red one here. And what I do in my approach, in this approach, is basically do this averaging for every possible orientation of the local coordinate system, and I do it for every particle. Right? Now, and when you do this orientational averaging, what you implicitly assume is that the structure around the particle is symmetric. All right? All we're going to do is we're going to basically relax this assumption, and we basically do the following. We know that fast particles hop out of their cages over the time t star, and what we're going to do is to take my coordinate system and align it along the hop direction. Okay, so this is my fast particle. And basically it moved at time t star along this direction. So what I'm going to do is I'm going to orient my z-axis along the neighbor that's closest to the hop direction. All right, and please note that I'm using this hop information. Okay, I'm using this hop information only to align my coordinate system. I'm going to calculate the structure around the fast particles at t equal to 0. That is before it made the hop. All right. So this is basically what we do. So this is going to basically probe a cage anisotropy if it exists. And what we find is we're going to compare it with the slow particles, which at time t star did not break out of cages. And this is the slow particles. Okay. Nice icosahedral, dodecahedral. Same is true for the hop, for the particles that hopped. But if you now see the difference is localized along the hop direction. Okay, what it's basically telling you is that the structural difference between the fast and slow is same in all other directions except along the direction in which the particle escapes out. Okay, so what I can do now is render these density fields. So that's what I've done. So I've taken the difference between fast and slow, and I'm rendering these density fields. And this is the central particle, which is the one that makes the hop. And you basically see this sort of an anisotropy in the cage structure, all right, at t equal to 0. And as you cool the liquid, this structure basically grows, all right. And what one can do now is basically, in principle, what it means is instead of doing spherical harmonics now, you summed over m in the earlier version. All you have to do is not sum over m because you now have an anisotropy that's built into the problem. But we can do something much simpler, which is just to calculate the pair correlation function along the direction that the particle made the hop. All right, you do that. So this is my HFR. And I'm going to now define 2 more length scales in the problem. So these are from all orientations. These are from directions related to the hop. So I can define it for the slow particles. I can define it for the fast particles. And what you find is, of course, the slow particles never went anywhere. So the zeta s and xi s should be identical, which is what we see. Except now, if I show you what happens for the fast particles, so this is the fast particle, right? You see 2 sort of kinks that are coming about near T0 and Tc, all right? And what I can do is I can use the xi total as my overall baseline and subtract it out of the fast particles. And now if I plot the cage structure asymmetry parameter, basically I see a maximum, one at T0 and one at Tc. All right. So everything that's contained in the structure about what's different at T0 and Tc, one needs to basically look at the asymmetry in the cage. All right. And we can basically understand why this will be happening. So I have 2 more minutes. No. Okay. So just to tell you quickly, look, when I'm doing this anisotropic length scale, I'm picking one of the directions. If I'm in the high temperature liquid, the particle could have gone anywhere, so which it means that zeta f and xi f are essentially going to be identical. But then when I start cooling the liquid, these channels start closing down. I will not have time to go into this work. So now the asymmetry is going up, which is why this anisotropic parameter is going up. And then we know that strings emerge at some point here in the relaxation process, and basically your anisotropy starts coming down again. And here there's a string to compact transition that gives you the second maximum. Okay, I can talk to you in detail later. All right. So the talk would be incomplete if I didn't do one uncontrolled extrapolation. So one can do that, and you can extrapolate the fast and the slow. And they kind of intersect at tk, okay, for what it's worth. All right, so that's my conclusions. These are ongoing work. I'll be happy to take questions.
Thank you very much for reminding us that small step can be a giant leap. So now the talk is open for questions.
So I think one confusing part of the results that you presented, Rajesh, is, I mean, I think by and large everybody agrees that whatever is happening around the mode coupling temperature is a gradual change, right? But your results say that there's something discontinuous going on, and that seems to be not here, but in the earlier analysis, there was a jump, right? So,
so within what we can resolve, yes. I don't know if it is this or it is this.
Okay.
Yeah.
So I shouldn't take home the message that it's a discontinuous change. Okay, that's what
I wouldn't be able to say it from what we have. I mean, to resolve a step, you really need to go finer. Yeah.
So Rajesh, right here.
Yeah.
Hiding here. Yeah. So if I understand what you are trying to put forward here is that G of R or static structure factor, so they are essentially an isotropic measure. So they cannot really capture the anisotropy of
Yeah.
the cages that you are trying to present here, and that's why you cannot see.
They cannot capture forget cages. They cannot capture the angular order because you averaged over. Even for the slow particles, which do not break cages, you do not capture it.
I see. So that is the point that you're trying to make here. Is that right?
No, no. Those are the points that we made earlier, not by me, but by Walter, and we did experiments confirming that. What we are trying to really see here is that, is there like a subtle order that changes across T0 to TC, and this analysis, when done along the proper orientation, seems to pick it up.
So I wanted to ask about the plot near the end with the anisotropy of the motion and the different regimes. Yeah, this one. So I sort of understood your rationale for the first peak. I don't understand why there's a peak for the
Oh, you
second
mean this one here?
The one at TC.
Ha.
The one, yeah. Or,
Ha.
Maybe with an error bars, no?
Okay, yeah, one could say that. Yeah, but what we think is happening here is the following. So we're still honing in the arguments. So what we know is that after T0, the experiments find, simulations find that your heterogeneities are predominantly string-like. And what we think is happening is that you see this compaction happen close to TC, which means that your strings have reached their maximal extension. They reach the maximal extension, which is around here, and beyond that there is this compaction which makes the cage more isotropic because it's a different sort of motion. And that's what gives you the second maximum.
Okay, I think we should thank Rajesh again for his nice talk. And we switch to the last speaker of this morning, who is Pinaki Chowdhury. And now I don't know the